In a factory, machine 1 produces 8-inch pliers at a rate of 60 units per hour, H, and 6-inch pliers at a rate of 70 units per hour. Machine 2 produces 8-inch pliers at a rate of 40 units per hour and 6-inch pliers at a rate of 20 units per hour. It costs $50 per hour to operate machine 1, and machine 2 costs $30 per hour to operate. The production schedule requires that at least 240 units of 8-inch pliers at least 140 units of 6-inch pliers to be produced during each 10-hour day. Which combination of machines will cost the least money to operate? So let X be the time used on machine 1 and Y be time used on machine 2. So knowing that, notice that we have each 10-hour day. So that means my X on machine 1 has to be less than or equal to 10. And for my Y, that also has to be less than or equal to 10. Now notice with machine 1, it says it can create 8-inch pliers at a rate of 60 units per hour. So if we think of that, X is the time on machine 1. So if I think of 60 per hour, I can think of 60X being the number of pliers produced, 8-inch pliers produced on machine 1. And we can also think of on machine 2, notice that its 8-inch pliers are 40 units per hour. So that would be 40Y because the Y is the number of hours on machine 2. So 40Y would equal the number of 6-inch pliers on machine 2, 8-inch pliers on machine 1, excuse me. So knowing those two pieces of information, it also says that the production schedule requires that at least 240 units of 8-inch pliers. So we need, this is all of our 8-inch pliers that we're going to produce per day, and that has to be at least 240 units. So together, that has to be greater than or equal to 240. So we get this inequality. 60X plus 40Y is greater than or equal to 240. Now similarly, we can find out the 6-inch pliers. So for machine 1, it says that for 6-inch pliers, the rate of 70 units per hour. So again, now we're going to have 70X, and that's going to be the number of 6-inch pliers produced on machine 1. And then for machine 2, where's that at? For 6-inch pliers at a rate of 20 units per hour. So that's going to be 20Y. And then it says that at least 140 units of 6-inch pliers be produced during each 10-hour day. So that means we're going to have 70X plus 20Y, and that has to be greater than or equal to 140. So this is our constraints here for this linear programming problem. Now what we're being asked to do here is it says which combination of machines will cost the least money to operate. So we're minimizing cost. So we have to go to the cost. Now this is going to be the function that we minimize. That's when we had the Z in the other problem. So it costs $50 per hour to operate machine 1. So what would that mean for us? That would mean it would be 50X. And that would be the amount for operating machine 1. And machine 2 costs $30 per hour to operate. So that would be 30Y. So now our cost function, call it C, is going to be 50X plus 30Y. Now we have all the information we're going to need here to actually minimize our cost. So our problem really becomes as simple as minimize C equaling 50X plus 30Y and all these constraints. So we're just going to graph these now and determine our feasible region. So two more equations or inequalities we have to add as well. Our X has to be greater than or equal to 0, and our y has to be greater than or equal to 0 as well, because we can't have negative hours. So that's something we have to take into consideration as well. So let's just graph those first. So that's just going to be the x-axis and the y-axis. So there's the first two. Not the inequalities graph, but the boundaries of those inequalities. So now we're going to do x less than or equal to 10. Now again, we're just going to do x equals 10. Now we're going to do y equals 10. And then 60x plus 40y equals 240. So for that boundary, I move the 60 over, so that's going to be 40y equals negative 60x plus 240, and then I would divide everything by 40. So these numbers actually turn out to be quite small once I do that. So I'm going to get y equals, and this is going to be, well, 10 goes in each of those, and that's going to be 6 over 4, and then 2 does. So that's going to be 3 over 2 negative x, and then plus 6, because 240 divided by 40 is 6. So that's what you end up with. So we're going to actually graph that equation and not the big 60s and 40s and 240s that you see in front of you. So the idea of graphing that line would just be down 3 over 2. And I would keep doing that all the way down that line. And my y-intercept is 0, 6, and that's why we started here. Okay, so the next line then is going to be 70x plus 20y equals 140. So now let's simplify that one just the same. So I'm going to move that 70x over, so I get 20y equals negative 70x plus 140. And then I'm going to divide by 20 everything here. So then my y is going to equal negative 7 over 2x plus 7. And we're just going to graph that line now. So that means we're going to start at 0, 7, because that's our y-intercept. That'll be here. And then from there, we're going to do down 7 to the right 2. So with x less than or equal to 10, I'm going to be on the left side of the orange one. And with the y less than or equal to 10, I'm going to be down here as well. Now I could still be even way over here on the right side of all of those. So we can see that okay. And then that 60 plus 40, I have to pick a value now. And also the last two are okay. The red tells me I'm going to be in the first quadrant. So that's okay too. And then now we have to just decide what it means to be 60x plus 40y greater than 240. So I'm just going to pick the point 1, 1. So that would be here. I'm going to pick that point 1, 1. And if I plug in 1, 1 here, if it's true, I'm going to be on the left side of both the purple and the green line. If no, I'm going to be on the right side of both of those, if it works for both of them, of course. So I'm just going to plug in 1, 1 here. When I plug in 1 here, for both my x and my y, I'm going to get 60 plus 40, which is 100, which is not greater than 240. So that means I'm on the right side of the green line, okay? And then I'm going to do the same thing with the purple line. I'm going to put 1s in there for both of those. And that's 70 plus 20, which gives me 90, which is not greater than or equal to 140. So that means I'm on both sides of the green and the purple line. So that happens. So there's our feasible region. Now we need our points, our corners of the feasible region. So this one here has a lot of points, because remember, we're in the first quadrant too. So we have one here, we have one here, we have one here, down here. We also have one over here, and then back to the center again. So that gives us 1, 2, 3, 4, 5, 6 points to find here. Now there's going to be a handful of these that are pretty easy to find, like this one here is 10, 10. And this one here is 0, 10. And I'm just going to find all the easy ones now. So this one here is going to be 10, 0. And this one's 1, 2, 3, 4. This one is 4, 0. And then this one here is going to be 7 or 0, 7. So honestly, we only have one to find that seems like we're going to put some work in for it. So that's the one where my purple and green line meet. So we're going to take these two equations here and do a substitution method, or we can do elimination method. So I'm just going to do substitution since they're both solved for y already. It's going to be easy to take like this, it's negative 7 and 7 over 2x plus 7 and plug it in for y in the other equation. And then I just have to get my x's on one side and my numbers on the other. So that means we're going to add 7/2 x to both sides. And then subtract 6 and subtract 6. So I'm going to get 1 on the left, and on the right I'm going to get, when I add those, are different signs, so I'm really subtracting. So that's going to be 4/2, which is 2x. And then I'm going to divide by 2, so x equals 1/2. So then I just take that and plug that into any one of the two equations. I'll plug it into the top one here, because it doesn't matter which one I plug it into. So then my y is going to equal negative 3 over 2 times 1/2 plus 6. And that's going to be negative 3/4 plus 6 over 1. And if I times the top and the bottom by 4, that's going to be 24/4 minus 3, which is 21/4. So my y equals 21/4. So then my ordered pair is going to be 1/2, 21/4. So those are all of our points. Now remember, we're minimizing here. So now we're just going to have to test all of those and find the smallest combination there. I should say the combination that gives us the smallest cost. So for the first one, C equals 50 times 10, times 0 plus 30 times 10. And that equals 300. Now 10 and 10, so C equals 50 times, not 50, but 10 plus 30 times 10. And that's going to be 500 plus 300, so that equals 800. So the third one's going to equal 50 times 10 plus 30 times 0, and that's going to be 500. So then C equals 50 times 4 plus 30 times 0, and that equals 200. And then C equals 50 times 1/2 plus 30 times 21/4, and that equals 365/2, which equals actually 182.5. And then the last one here is C equals 50 times 0 plus 30 times 7, and that equals $210. So we can see here that we're trying to minimize cost. So where we have 1/2, 21/4 is going to be our lowest cost. So our x equals 1/2, and our y equals 21/4. And 21/4 is really 5.25. And remember, we're talking about hours here. So this is a half an hour. And this is 5.52 hours, because remember, X was the time used on machine 1 and Y was the time used on machine 2. So that means if I use machine 1 for half an hour and I use machine 2 for 5.25 hours, that'll be the minimum cost in which, now remember this, where I can produce at least 240 units of 8-inch pliers and at least 140 of 6-inch pliers. So that would produce that minimum amount, and that would be the minimum cost for that. So then our final answer should read, to minimize cost, machine 1 should be used for 1/2 hour per day and machine 2 for 5.25 hours per day. So there's our answer.